Better be working.
We're not getting, you're not getting any rich.
So this is a project I worked on for school in 2008. I actually I saw this meetup about zippers and I was like, oh, zippers, that's great, because I played with those a long time ago. I just yesterday recovered the Keynote file that was really, really old and wouldn't open in modern versions of Keynote. So I had to find a machine with Keynote 09 so I could then open it up and resave it, then open it in my machine and resave it again.
Nice.
So the goals of this project were to implement the zipper data structure in a tool called Coke. Has anybody heard of Coke? Okay, awesome. So it's a proof assistant, which I guess we'll get into what that means in a minute. But the goals were for a zipper implementation, prove that for any possible input, so any tree, any modification function, that the program would terminate, which is usually a relatively hard property to show. And then there's some other specifications I wanted to prove as well. Do a little bit of comparing and contrasting with Quick Check, and then automatically generate code that would kind of preserve those specifications. So generate code that I could prove would always terminate no matter what you did. I'm going to skip through a lot of this because it's kind of an introduction to what a zipper is. And we already just went through that. So Xmonad uses zippers, ZipperFS, which is currently an old project because this is an old presentation. E for text editing, and then data tree AVL in Haskell. So yeah, that's some pretty pictures I think that try to show what a zipper does. And I think, I don't have my notes for what I was saying here, but I think this was demonstrating how difficult it is in a functional language to change like to, because you got to go up to its parent, and modify all these things and reconstruct the path. But with the zipper, so this top thing is the zipper, the thing to the right is the start of that breadcrumb, also called a context. And this T means it represents the top of the tree. So now when you hit that thing, you know, instead of like the empty list, you know, hey, this is a special marker that says, hey, I'm already at the top, so this thing on my left-hand side of the zipper is the original tree. Oh yeah, okay, focus, context, and top. So moving right, get that right instruction. Moving left, place out the left instruction. And so this is kind of, in my mind, was illustrating, okay, that starts to look like a zipper. You know, I've taken this tree, and now it kind of just flows into this zipper structure.
It's a much better visualization.
This is why I had to recover this Keynote presentation because the PDF version of this did not work. And then you can unzip it. And then, of course, if you want to go back to the tree, you just go to the top and then throw off all that extra zipper stuff and you're back to where you started. Okay, so for me at least, when I learned Haskell, that was kind of a mind-blowing thing, right? This language that was more like math than programming. And then when I learned Coke, that was kind of like another mind-blowing experience. Just like, oh wow, I can now write proofs about my programs, and I'm not really programming anymore. I'm just writing proofs, and then the programs just kind of emerge from that. So it's kind of like another level to programming. So in this system called Coke, instead of writing the program, you write a specification, and then you prove that specification can really exist. And in those steps of proving, you kind of, as a side effect, are generating a program. So it's like it's kind of like test-driven development. You start with your tests, right, and then the program kind of emerges from that. This is the same thing, but kind of in a much more automated fashion, in a way that you can get assurance at every stage that you are doing things correctly. So the specification that you're writing, that you're going to prove, is in a functional language called Guyena, which is a total language. So unlike Haskell, where you can write like incomplete patterns, you can't do that in Gaia. Every possible data structure you can encounter, you have to say what's going to happen as the next step when you're writing the program. So you can't have kind of holes that you just say, oh, that'll never happen, right? Don't worry about that. The compiler will stop you and say, no, your pattern is not complete, so you must put code there because I can't do anything if I don't know what happens. So once you get your specification, you write some kind of statements that you want to prove about it, and then you use things called tactics to transform those specifications into your proof. And I'll go through a few of those. Oh yeah, an important note, Gaina is not Turing complete. I can't write arbitrary recursive things in it. I have to show at every state that I make things smaller when I'm recursing. So that makes a lot of programs hard to write because it'll say, you know, this thing you're passing back into myself is not obviously smaller than the thing I started with. Doesn't type check. So you have to kind of prove that these things get structurally smaller. And just stop me if you have questions.
Is there a way to lie to Gaina and say, no, just trust me, it gets smaller?
So, not really. There are some tactics that you can use to say, trust me for now.
Okay.
But when you finally come to that last step where you want to say QED, it'll say, no, you're not done yet. I don't have proof for this proposition, so I can't do anything. So you can just say, like, hold on, wait, trust me for now. But it will always come back to you and say, hey, here's all this stuff you said, trust me, that you haven't proven yet. So, and it's not, it keeps track of that for you, so.
Yeah.
Okay, so specifications or types. So this is a specification that says for all trees, it is always true that a tree is equal to, so this location of tree and tree location are the things, I believe, where you are converting trees to zippers. Okay, and so this is saying that for whatever tree you give me, if I take the tree and convert it to a zipper, and then convert it from the zipper to the tree, that's going to be exactly equal to the tree that you started with. So it's kind of a very obvious property. This is just kind of an example of how to do a very simple proof, because this should be obvious. I mean, you could write a location of tree or a tree location that wouldn't work, but in this case, it should, just add an element, add that context, and strip the context away. So, so in Quick Check, this would look very similar. So this top one is the Quick Check version where you've got a property, location of tree location t equals t. So if you think about it this way, the propositions, the specifications look very much like what you'd expect to see in Quick Check. They oftentimes look identical. Now Quick Check, sometimes you have to tell it how to generate these arbitrary instances so it can generate them and do the comparison. In some cases, you don't even have to do that with Coq. So Coq can be even quicker than Quick Check. And you'll always know with Coq, like once it says it's done, like there's no counterexample. It's proven. So this one here, that location, tree location, Coq will prove automatically for you. Put that in there. You use a tactic called auto. You'll try some random stuff. You'll say, oh yeah, this works out very easily, and you're done. The next specification I'm going to show can't be proved automatically by Coq. So this is what Coq looks like. This is a front end called Proof General, I believe, and so it's just an Emacs add-on that allows you to work with Coq down here. This is the program I'm writing, and this is Coq, which is the interactive part of it, guiding me through that proof process, showing me what my current goal is, how close I am to it, and as I transform stuff, what that result is. So let's see, this one is saying that for all trees, for all, I guess that's, trees and functions that modify trees. This is like the modify function. If I apply that tree modifying function to my focus, it's the same as if I got the focus and then modify with that function. So again, it's kind of showing that modify is the same inside a zipper as it would be in just the tree by itself. So that's the specification that's highlighted right there. Yeah, okay. The tactics are the way that I'm going to transform that as I go through. Assumptions of my proof, I have none right now. This is what I want to prove. This is the statement that I had up there. So this is basically like the code I want to prove is true. Let's see, the intros tactic will strip off those for alls and turn them into variables. So I had that for all for location and that modifying function. That pulls them off and gives them names. And then now this is no longer a for all. This is just a quality, but these are givens. Let's see, destruct L is going to replace, yeah, so that L function I had, you see at the bottom in that goal F, get focus L. Destruct L is going to take L and replace it by its definition. So that makes things look worse for now because I've added a lot more functions down there. Let's see, unfold, get focus. Let's see, I don't remember exactly what unfold is doing here. But I guess it is
Are the
also expanding it.
things that you also wrote, or are those things that Coke is giving you?
So the top pane is all stuff that I've written. The bottom pane is all things that Proof General that Coke through Proof General is providing me.
I'm just trying to understand, like, what are the
Intros and
keywords
destruct those.
Okay, so those are tactics. Think of those as,
But you wrote those.
no, those are built into Coke. That's what Coke gives you is the
okay.
tactics.
Okay.
So it's proof steps, very small proof steps. Some of them are smaller than others. Like there's a tactic called auto, which does magic and tries to apply a lot of different stuff to try to find a solution. So it's kind of like an automated proof solver. But it doesn't work on very complex things, obviously. So some of these are more complicated than others. Intros is very simple. It just pulls off for alls and introduces variables. I forget exactly what unfold does, but the Coke documentation kind of gives you a list of all these hundreds of tactics that they have. And part of the difficulty using Coke is just reading through all those things and understanding what is a good, because you gotta like relearn how to write a proof in terms of these tactics, and some of them are very complicated what they try to do. But the basic idea is that I'm running through these things which are modifying my goals, adding assumptions, and I'm trying to get this to be something that is trivial, like A equals A, right? Okay, didn't say QED because that's obviously true. This right now is not yet obviously true, so I just keep applying more tactics to try to get to a true statement. So change is it's kind of a complicated one, but it's basically saying rewrite this based on the fact that some of these things are kind of trivially true. So it's replacing some things, but in a way that Coke can validate for me. And now this is kind of the step you want to get to, where you say, okay, function applied to some value is the same as a function applied to the same value. That should be true just by like the reflexive property of equality, which is what that apply function to do. So apply will take some mathematical law and say, hey, see if this is the same as what I've got in some way. It does that, so now I can say, okay, we have no more goals remaining, and QED, now it says this modify subtree arbitrary is defined, it's happy with it, you can use it now in your other programs, before you couldn't. And you can actually print that out, and now you get the, so here's the funny thing. The thing at the top, that was a type. What it's given me is a program. So all I did was make a type, show that there is some value that inhabits that type, but I didn't say what it was. And then Coke says, okay, here's a value that inhabits that type. That's the program. So again, it's kind of a very different way of programming, because when I was doing this, I wasn't thinking about, and I didn't even really, I wouldn't have been able to write this. I wasn't thinking about this. I was just thinking about proving that statement and what that statement means.
Question.
Yeah,
Get focus, is that a function that's built into Coke? Get focus?
No, focus is a function that I wrote.
Oh, okay.
This get focus. So what you don't see here is that get focus, modify, those are functions written in Guyena behind the scenes. And I'm using those and I'm proving properties about them.
Okay.
So, yeah, so recursion is the funny one. If the value that we're recursing over is always smaller, if I can always say, hey, I've got this thing, strip away this and recurse on this thing that's inside of it, you're good. If the function is more complicated than that, then it won't work. So this is an example of move to top, which would be like that up function that we saw. Like instead of just up, I think it moves all the way up to the very top of the tree. So it basically gets you in a state where your zipper becomes the same tree that you start with. So this is an implementation that would work in Haskell. The tricky thing here is that if you write it a very slightly different way, it is still well typed. Haskell's still happy with it, but it never terminates. And so this is the sort of thing you have to read and look at it and think really hard about, okay, which way is the recursion working, and what's the right way to not run forever. So that can be tricky. Yeah.
Would you not get like an ambiguous pattern matching error or something on that?
In 2008, on the version of GUC that I ran this on,
Okay.
I'm pretty sure that it was happy with this, that
Okay.
you get you may get a runtime error, maybe,
Okay.
but it
Yeah, I was just wondering because when I was writing some of those functions like up or left or whatever, I ended up duplicating stuff, and I was like, oh, I need to do this. I know I need to do this, but Haskell's like, no, you don't need to do this. You've already done it and stuff above. It's like, okay, all right, never mind.
yeah. And I mean, in practical terms, a lot of these safety checks Haskell
Yeah.
has for you. But there are examples where recursion is, you have to look at it and you have to analyze it outside of Haskell.
Yeah.
Haskell can help you a lot of times, and by telling you when you get incomplete patterns, that's another helpful thing that you can turn off if you don't want it. So one of the problems with move to top is that this recursive step isn't obviously smaller. Right? I'm not taking L, deconstructing it, and passing some child back in. I'm taking the whole argument and doing more to it. So if you look at this from the compiler's point of view, it's going to say this could be getting arbitrarily large. It can never terminate. It can just run forever. It doesn't have any way of knowing that it's going to terminate. And so the solution for that in Coke is to do something I think is called bounded recursion, where you write that recursion statement the same way, but you provide a function to the side which can measure the thing that you're working on and give sort of a complexity argument for it. So it can say, for example, well, this move to top is going to need 5 steps because we're 5 steps away from the top. And you can use that as kind of a side way to show that this, maybe this function doesn't look like it's getting smaller, but on the side here I can show that this count is actually getting smaller. And then you just have to do some proof to show that these things are equivalent, and you can kind of sidestep that recursion issue. Yeah, this is just a demonstration of this counting mechanism. I'm not sure if I have code for that here. No. I do have it in a text editor I can show you in a second, but this is just a long way of saying that even with complicated recursion, you can still use Coke to validate it. You just have to do some extra work on the side. So let's see. In this project, I did some proofs to show that you can convert back and forth like we saw, that move right and move left do what you expect as far as getting different parts of the tree, that when you run modify, the only thing that can be touched is the focus. It can't go and change the context. So you can have some safety guarantees there that you're only touching the part that you think you are, and you're not accidentally kind of escaping and going off to the side. And that move up doesn't do anything once you go to the top. You can prove that there's no errors or other weird things. Okay, so yeah, at the end of the day, you want your programs to run somewhere, presumably, and not in some weird proof system. So one of the features that Coke has is you can take your proven specification and then export it to real code. Scheme, Haskell, OCaml, maybe more today, but I haven't checked. This was an example of the export from the program in Gaeta to OCaml. I think that's the only one that I have here. It's not a whole lot different, but the nice thing is that you can say, okay, the person didn't write this, this was automatically extracted, as long as you trust the generation program, which I'm not sure that's been formally verified, you're safe. That's always the catch. In the real world, the logic I use to prove that recursion step is now embedded in the OCaml code. And that was like a Pinot arithmetic sort of thing where I was building structure for counting up how tall the tree was. Very, very inefficient. This is probably hundreds of times slower than it would be if you just wrote it in OCaml yourself. So you got to ask yourself, is the verification worth, 100x or 1000x performance hit?
What is that word? Piano?
Pinot arithmetic. So it's the idea that instead of using, when we talk about structural recursion, things like that, you can't just use a number. You can't just say, oh, 3. And why is 3 bigger or smaller than 2? There's values in memory. In Coq, you're going to use recursive structures built up from data types. So 0 is a data type, and you're gonna. It's kind of like counting by having a list of things. And instead of representing that list of things by a number, you're just gonna say, oh no, just traverse this list, and when you reach the end, that's the number that it represents. And so representing a number like 50, you can't do it in a byte. You got to do it in 50 con cells that are linked together.
Okay.
So
It's a very small set of axioms for representing integers. So,
yeah.
Okay.
But it gets you, so it lets you prove things much easier because you can show that these numbers have a structure and it's not just some bits in a memory cell. It's actual structure that will grow and shrink, and you can then use that for your easily proven recursive functions.
Okay.
Like, remember, was it last month or the month before we covered transformers, monoid transformers? And I was saying that, you have to lift a bunch of things from nested monads up to the top in order to get them to sort of run properly. And you have to know how far deep you were. But one way of sort of encoding that is in the type system itself. You say, oh, because I'm monads down, because I'm 3 types down,
Yeah.
but since I had to get there via cons in the type system, I now know I have to lift 3 times.
Yep.
And so libraries can do that automatically for you.
Okay.
Yeah, so it's ridiculously inefficient to do in a programming language, but yeah, it is almost impossible to write buggy code. It's also almost impossible to write correct code. It makes you think really, really hard about your problem. So instead of this being like an afternoon project to go, I'll go write a zipper in Haskell, or a few day project, right? It's like, oh, this will be a month-long project. And I'm not sure if there's any, oh yeah, so, oh, this is just an arbitrary generator for trees that I configured. So questions? I do have the full Coq file I use for this, which is about 300 very small lines. I don't know how to see. Command Shift plus.
Control X plus or Command X, whatever it is, plus typically works. Not here.
Dangers of using Emacs menus.
I was just using Emacs in a terminal.
There's a zoomy thing in Mac, isn't there? Like a shortcut to zoom your screen?
There is, yeah.
Yeah, I'm pretty sure there is. I don't remember. You know what that was telling me yesterday? Someone was using either Douglas or you.
There's a command plus, but that's for usually for other applications. I mean, that maybe works for Emacs. I don't know.
I mean, like in OS X would actually zoom in for you.
Oh, the whole desktop.
The whole desktop.
Yeah, you can zoom in, but I don't remember what it is.
Yeah, I thought it was like Command Option and then maybe like
Yeah, no.
Anyway, if anyone's interested, I can give you a copy of this, because it kind of has a lot more notes about all this stuff. And then I think at the bottom here, I've got a lot of the proofs, the combination of the tactics that I go through. So yeah, I did this in 2008, and I haven't really touched Coke since, which shows you how practical it is. But it is sort of a mind-expanding exercise to take a simple specification and turn it into a program just by kind of tweaking the type instead of having to write the program out. Okay, so questions, I'll close this guy down. That's pretty cool.
Thanks.